Okay, hello everybody. Welcome back to the Intercontinental Seminar Series of Gravity and Cosmology. So today we are very happy to have Professor Florian Kühnel to give us a presentation. And Professor Kühnel, he got his PhD in Bielefeld University in 2009, and right now he's a professor in Technical University of Dortmund and also Maximilian University of Munich. So without further ado, the stage is yours.
Wonderful. So, uh, many thanks to you and all the organizers for first of all running this wonderful online series, and in particular for having me here and talk about my most favorite subject in physics, because this is what really excites me a lot. And I will tell you about what my take is, and I have a very positive view on this, or positivist. I will tell you what I mean by this. And I will tell you about of course, the basics of primordial black holes, and then sort of what hints we may have and why we may search for them, and a bit of quantum aspects of their, you know, uh, well, formation and existence, and also what role they may play in galaxy formation. All right. But first things first, let's talk about some historical remarks. So just first, when I talk about primordial black holes, I mean really black holes. So I don't really leave general relativity, it's black holes. But those produced in a non-stellar way. So usually stars, of course, black holes are usually produced in astrophysics, at least at the end product of a star which was heavy enough, probably not too heavy, because we will come to this pair instability mass gap also possibly later. But I mean, of a star in a mass range, you produce a black hole. But of course, that limits also the range of the black holes and the time when the black hole comes to being. But these primordial black holes are produced in the very early universe. When I say very early universe, I mean very early universe. Very early meaning maybe around the time of the QCD transitions, probably 10 to minus 6 seconds after the Big Bang. So it's something that it occurs usually deep in the radiation-dominated epoch. Ironically, the very first paper, which was by these two gentlemen, Novikov and Zeldovich, stopped research on these objects for quite a while because they concluded these primordial black holes, which they didn't call primordial black holes, but these black holes shouldn't exist because of catastrophic accretion. It turns out that they made a mistake. The mistake was using Newtonian physics, and then he found a catastrophic accretion. But actually, these two gentlemen, my friend and collaborator Bernard Carr with his PhD advisor, Stephen Hawking, they, really brought this back to business, and they corrected the mistake. And now we have thousands of papers, and they're really back in the game. They don't accrete catastrophically. So this is, since the mid 1970s, they are back in business. Right. How do they form? Now, this is an incomplete list. It's a longer list, but it's an incomplete list. But what all these mechanisms have in common here is that you need a large enough overdensity. Then GR, the relativity, will individually produce a black hole once you have, bring a configuration within its Schwarzschild horizon. So it's a hoop conjecture. No? And you can get overdensities in multiple ways. For instance, you have something that is morally similar to what produces the CME fluctuations. But think about these fluctuations of inflationary origin being, at much earlier times, at much larger amplitudes, such that a certain patch collapses to a black hole. You will have a whole Hubble patch basically collapsing, but Hubble patch, way back. This is sort of assisted by a reduction of pressure, because you have radiation pressure, because in the radiation-dominated epoch, usually when you reduce the pressure, you will usually make it easier to collapse. So reduction of helps, and that's actually an exponential enhancement of the abundance. You can also have cosmic strings. You can have these strings can actually self-intersect, and with some probability, they will come in their own Schwarzschild radii and then produce a black hole. I think even Hawking worked on this. You can have another mechanism to formation of bubbles. You have first order phase transitions, and so these bubbles may collide. And then you can also get under certain circumstances, usually with tuned circumstances, to get, large enough energy densities to get a substantial amount of black holes at present times. But of course, there you need to have that the bubble formation rate and the Hubble rate are basically on par. Otherwise, in one extreme, the universe expands too rapidly or the bubbles expand too rapidly. So you will not get too many black holes left in this mechanism. I worked on a mechanism together also with Quiddity. We proposed this to produce black holes from quark antiquark pairs. I can tell you later about this, but there's a zeta fluctuation producing quark antiquark pairs, and in certain conditions, if the string, the flux tube doesn't break, you could get those objects colliding and producing a black hole. But there are many other mechanisms. Like this is actually a relic from a talk. I apologize because it's a talk by it was in a conference and there was talks by Dieter Löstelmann and Eppengruber. They talked about higher dimensional scenarios and many species scenarios. There's a lot of scenarios which you can invoke, and this is not a complete list, as I said. But again, all mechanisms have in common that you need large overdensities, and this is sufficient. If you have large enough overdensities, you make inevitably black holes. And therefore, it's a natural candidate for the dark matter. And you don't need to introduce per se a new particle, even though some of these mechanisms involve more degrees of freedom. But per se, and in principle, in the most minimal setup, you may get it even from the inflaton field. So that you may not need actually new degrees of freedom. So that's an exciting possibility to get dark matter in a relatively natural way. Now, here's a simple picture of our universe when we have scales leaving the physical horizon. So I put here scale versus time measured in number of e-folds. Here we have the Hubble scale, Hubble horizon. Here is the gray line. We have this phase of course inflation, then phase of reheating, radiation, matter-dominated epochs, and then something that looks like a cosmological constant. We have a scale, physical scale, of course, being redshifted outside of the Hubble horizon during inflation, and then coming into into causal contact again. When only then the collapse can happen. And of course, if you have an overdensity, then which is above a certain threshold, that it sort of collapses on its own gravitational attraction, then you can get a black hole. And the threshold, of course, is very crucial here. But also what you observe is, when this happens at a later time, so suppose the re-entry is at a later point in time, it happened actually earlier. So the fluctuation left the horizon earlier. So if you think about black holes probing early times, which in this mechanism in principle you could do, you could think of black holes were produced in the early universe, like early radiation-dominated epoch, but in this mechanism, suppose it's true, you want to probe the early, even earlier epoch, like inflationary potential, say, then you have that black holes that produce later, and which are also then heavier, because an rough indication for the mass of these objects and that mechanism is that the mass contained in one horizon patch is roughly the mass of the black hole. So re-entering later means re-entering in a bigger universe or larger horizon patch with more mass, so the black holes will be heavier. So heavier black holes probe earlier times. Heavier black holes probe earlier times. It's sort of easy when you think about this, but it's it's something not so well thought of. Anyways, this is sort of the schematic picture in this sort of most discussed mechanism to produce these objects. Now, well, how does it compare to our beloved CMB? So if we have the map of cosmic microwave background fluctuation, which this is a picture from the Planck mission, which probably most of you have seen multiple times. And we have these small fluctuations, and we can learn a lot about the universe, but we learn basically about the last 10-ish e-folds at maximum. But when we look then at the scales relevant to primordial black hole formation, and here I drew the primordial power spectrum, which is nearly flat, but a little bit tilted, and then, but the amplitude of the primordial curvature fluctuation spectrum is about 10 to minus 9, which is not enough to produce black holes. You need to go to 10 to minus 2. There's cases where you need much less, but in a large class of cases, you need to go to 10 to minus 2. And in any case, you need to elevate the amplitude quite a bit. And if it's large enough, you would produce a black hole. Now, this is, as I said, a number of e-folds here. And the number of e-folds, of course, goes exponentially through. So e to the nt in some sense. So e to the ht, sorry. It goes exponentially through time. So it's many orders of magnitude between these CMB scales and primordial black hole scales. You're not per se in conflict, even though in some cases with some nonlinear mode coupling, you can have effects visible in the cosmic microwave background. Right. So now one thing is these things happen very rarely. So when you look at the statistics and you suppose this is the probability distribution for density fluctuations, and suppose I start with the Gaussian fluctuation. Here I put the density contrast. So delta is delta rho over rho. Put it here. How much you're above the background with your energy density. And if you're above a certain threshold, delta C, which depends on the medium. So I said when you have a reduction of pressure, you will have, of course, a more preferred condition for collapse. And so depending on where this delta C is, you would produce black holes in larger or smaller amounts, or not at all. But usually you see, as long as your tail extends to infinity or to very large values of the density contrast, you will always produce black holes. Even the CMB spectrum, if you don't do anything, would produce primordial black holes, but very, very rarely. I mean, exponentially suppressed. But still, you would produce a black hole somewhere in the tail. Now, typically, we talk about like 10 sigma fluctuations. This is really rare. And but if everything is Gaussian, you know the fraction of collapsed horizon patches, I told you the scale fluctuations re-enter the horizon. There's a collapse, and this collapse of a certain horizon patch happens, somewhere in the universe. And this, in this Gaussian case, is really exponentially sensitive to the threshold, which can also be seen here. So if I move this a bit to the left, I get exponentially more black holes. If I move this a bit to the right, I get exponentially less. So it's exponentially sensitive. But I must say, since in many circumstances, in these inflationary scenarios where you have certain features in the inflationary potential, not just the classical fluctuation, but also the quantum fluctuations become important. And in certain cases, you need to do these quantum diffusion calculations, which actually makes the tails much more shallow. So they follow sort of an exponential distribution. And that is, of course, much shallower. And you can increase the number of black holes quite a bit. So it's a matter of active research now. And it's interesting what we will see. Maybe we don't need this much elevation of the amplitude of the power spectrum. Maybe we don't need too much at all. So that would be it's an exciting direction of research. So it's just upshot, it's rare. It's rare events, and it's really rare. I tell you on one of the next slides how rare it is. So this is exactly one of the right plots for this. This is a map of constraints. And here we show the fraction of collapsed horizon patches, beta. So it's how many horizon patches underwent a collapse to produce primordial black holes. And here we have masses in grams on the lower x-axis, and the upper x-axis is solar masses. So you see it goes from basically the Planck scale up to basically 60 orders of magnitude above the Planck scale. So this is a huge range. Now, and everything above those lines is meant to be forbidden. And actually, particularly it's forbidden. Let's focus on this black line here. This black line means you saturate today, because that's at formation, but today you would saturate 100% of dark matter in primordial black holes when you sit on this line. This line is also appearing here. And suppose you sit here at 10 to 20 grams, so asteroidal mass range. Suppose all of the black holes are as heavy as typical, or some asteroids at least. You look at this. You have 1 in 10 to the 15 horizon patches that underwent a collapse to give you 100% of the dark matter. Now, that is what I meant. It's rare. And that's, of course, due to the fact that, you have radiation in the background, but this radiation is converted into a black hole in parts where the collapse happened. And that black hole scale dilute as matter. So the radiation dilutes much, much quicker. As one part of the scale factor, A is the scale factor. 1 power of the scale factor quicker than primordial black holes. And then sort of you get this sort of linear independence. It will deviate from that towards the end, but it's more or less this straight line, which you see. These are how constraints look today. As a primordial black hole dark matter fraction, one means you have 100% of dark matter, and in primordial black holes, and there's some So now, and there are a couple of constraints. For instance, you do have evaporation constraints. I will talk about those later because I don't think they are too meant to be, or they're not meant. They're taken with a grain of salt, let's say. Then we have lensing constraints, and everything in this shaded area is meant to be excluded. I have my take on these constraints as well. There's accretion constraints, large-scale structure constraints, and so on and so forth. So there's a bunch of constraints on primordial black holes, but there's a pretty much open window. But let me mention that this is for monochromatic mass functions. So everything, all dark matter at one mass. In realistic scenarios, you have an extended mass function. These constraints need to be recalculated. Also bear in mind that all of those constraints have assumptions going into those, and some of them, for instance, many lensing constraints disregard an extended mass function, disregard clustering effects, because typically we currently work on this. Black holes should be clustered and heavily clustered already because they're discrete. You get Poisson fluctuations in the number density, and these from the time of matter radiation equality until today would form veritable clusters. So, and it's very different when you look for microlensing events, whether it's homogeneously distributed or you have clusters, say, of 1 million objects. It's completely different. And therefore, all of these lensing constraints need to be read with the assumptions in mind imposed for the formulation of these. So just to say. And also one thing, this is an idea actually from Garcia Bido, who drew attention to the fact that all these constraints here are actually not just emerging from physics for one particular redshift, but also at multiple redshifts. So it's a projection. This is what you should keep in mind. Right. Now, let me perhaps very briefly mention another important subject. What happens actually when you do not have primordial black holes as being all the dark matter? Suppose you have some of them, but not all of them. What would happen then actually is that if you have other dark matter, suppose you have particle dark matter around, these particles would be accreted, would be captured, gravitationally captured by the black holes, and they would form halos. Now, if it's WIMPs, actually, the WIMPs would then annihilate because you get this halo around, and the WIMPs would form, so soon after kinetic decoupling, a halo around the primordial black holes. You get density spikes, and the annihilation rate goes like the square of the number density, and that would actually then lead to emission. And well, and then you can proceed as follows. You sort of compute first the halo, you compute the gravitational capture, and you have a halo profile. You compute, the annihilation rate, and you can compare this to data, say Fermi data. You look at the gamma rays which should come out of this. Okay, and here's a few lines, and this is sort of these two graphs, these two panels show the WIMP density. Rho chi means WIMP density. Versus radius, where 0 is in the center, and sort of its Schwarzschild radii are depicted with these vertical lines. And then you get different line types here of the colored lines. There's an initial profile. So when actually the halo formed, it's massive. You see, it's a logarithmic scale here. So you do have many orders of magnitude enhancement of compared to the background in any case. And then the WIMPs will annihilate away and plateau out. So you get, and this is the initial halo, and this is the halo today. You get a plateau, and then it falls off. And basically the slope here is r to the -9/4, the secondary info if you're interested. So, and you get this for different, we do this for different masses. This is a solar mass, this is a million solar masses, and this is for planetary mass, and this is for 10⁻12 solar masses. So you see, you can compute for different masses of the black holes, the halo profiles. Okay, initial halo profile, then they would sort of change from initial time to today. And then you have, you can have halo, which should be present today, and you can see what you can observe and what you get for constraints. And now look at this. This is incredible because it shows you that there are strong constraints and constraints on both. This scenario has primordial black holes as dark matter and WIMPs. So primordial black holes plus WIMPs make all the dark matter. So what is not in primordial black holes is in WIMPs, okay? And vice versa. And then we have different WIMP masses and the standard velocity averaged cross-section of around 10 to minus 26 centimeter cube per second, different WIMP masses. So this is all S-wave. You can do this also for P-wave, but this is S-wave. And then you look at the extragalactic gamma rays and see what you don't see. So because you don't see this excess, and you can limit the number of primordial black holes given the rest is in WIMPs, and with this type of WIMPs that I mentioned. But look at this. For a large part of the parameter space, it's basically flat. So, and it's basically not only flat, it's extremely low. That also means that suppose the LIGO black holes, most of them or part of them, or LIGO Virgo Kekra, let me better say this before the Virgo and Kekra collaborations come to me. So the LBK, gravitational merging black holes are primordial in origin. Then you would not have them being a dark matter fraction of these black holes 10 to minus 9. They would be maybe like 1% or 10%. That means if LIGO, Virgo, Kekra, if they or whatever gravitational wave detector, if they discover primordial black holes, then you can basically exclude all standard WIMP scenarios, and vice versa. So this also goes vice versa. No, it's a mutual exclusive scenario, which is actually a quite remarkable statement, and it's a very strong statement. Of course, if you crank down this cross section to whatever low value, then you cannot the bounds get weaker. But you see, you have to do it really, really, really a lot, or you change the masses you make the WIMP super heavy. But you see, there's a TV WIMP. You can go to PV, whatever. Then you change it somehow, but you need to change it. You need to turn the knobs quite a bit. So PBH and WIMPs, as a standard WIMPs, are basically mutually exclusive as being both 100% of the dark, both together 100% of the dark matter. Right. Now I talked a lot about constraints and formation. Let me come to what I find really exciting. I mean, really, really exciting is the prospects for their discovery and what we might have already seen. So that's why we called our paper Positive Evidence for Primordial Black Holes. And we said it's a positivist perspective because it is, there's this logic positivism, this stream, which has been formed a bit out of fashion in philosophy, but actually it's, instead of making too many deductions and putting too many assumptions, and formulating constraints, what we do, we look in the sky some people look in the sky and we take the results, but we look at the data. We just see whether there are phenomena where primordial black holes are probably the best candidate to explain them. And there are actually a number, and due to the brevity of time here, I can only go through a few strong ones, which I find particularly exciting. Now, first of all, primordial black holes are gravitational compact objects. They're heavy, and they would deflect light. So they're subject to microlensing. The source somewhere, black hole in the middle, and you observe it. The light will be sort of modified. And of course, usually it's microlensing, so you don't see the split of the images. You just see enhancement of the light curve. And you will, from the time scale of this sort of enhancement of the light curve, you will, and when you sort of know where the lenses are and the velocities, you can deduce the mass. Now, Ogle, so it's a Polish survey, they observed two populations of black holes with long light curve timescales, which are basically attributed to what we know astrophysically. So main sequence stars, brown dwarfs, and so on and so forth. But they have also a population of with timescales of hours. And this is in the planetary mass range. Now, you could say, very good. These are free floating planets, but hold on. If you look how many you need, you would need actually about 1% of all the dark matter being in free floating planets. And these people didn't come really from the primordial black hole side, but they said this is our best bet, that this is sort of some compact bodies like primordial black holes, which have caused it. So you need, you see, this the blue region is actually not an exclusion region, but it's a region where you, if the primordial black, in order to explain these events, you would need to have primordial black holes sitting there with this abundance, so say 1% around the planetary mass scale. Then you can explain those events. That's exciting because there seems to be not another explanation. And there's wonderful work by Mike Hawkins, who wrote a lot of papers on this subject by quasar microlensing. So he found now in a different mass range, in stellar mass range, microlensing of quasars. Now, you can think, okay, very good. It's in stellar mass range, maybe stars. But actually, he found those events where actually you would not expect stars. In some regions, the probability to find a star was 10 to minus 4. And yet he found those microlensing events, and he concluded that the most plausible candidates for the microlenses are primordial black holes. Because all of this, none of this is actually proof, but I will bring you some of these observations which we have made where it's at least conceivable to have these compact bodies causing them. All right, okay. What I find extremely exciting is a type of supernova that, could give us also an indication. But first, let us look at a more known type of supernova. It's a type 1a, which we all have heard of, our standard candles, and we have measured them like in large amounts. So here I put the cumulative event rate versus galactocentric distance, and this is sort of what you get. You get the distribution is measured type 1a supernova. I think that's probably even more than just the dots or just the ticks you see here. Okay, and then you look where actually are the stars, and the stars are here. So the stars basically, both curves basically overlay each other, and you have of course, as it should be. We think it's exploding stars, so they should actually these supernovae should occur where you have stars. Okay, fair enough. So we have this is fine, and there's probably not too much new in here, but type 1a supernovae are not our only type of supernova. There are actually multiple types, but in particular, a recently discovered one is the so-called calcium-rich gap transient events, which are spectroscopically and morphologically different. And look at where they lie. They are at completely different locations than the stars are. Then you can think, what is it? What could have caused it? And actually, the very same signatures you could get from exploding white dwarfs. So white dwarfs, think about it as this nuclear bomb hanging in space, waiting for an explosion, for a trigger. And you could trigger a white dwarf explosion by depositing enough energy into it, and then you can have those explosions that could have mimic those or explain those calcium-rich gap transient events. And then you can play the game. Okay, suppose in our galactic halo, I was to put, compact bodies, say primordial black holes. They're somewhat distributed in our galactic halo, dark matter halo. And where would they meet these white dwarfs, and where would they trigger the explosions? And actually, it's there. So this is absolutely fascinating, I find. I mean, we don't have yet too many data points, but we will get more soon, hopefully. But I mean, we have now, I think, 8 or so. But nevertheless, if you think about where would those explosions be caused by compact bodies, say primordial black holes, it's exactly on this line. And so this could serve as an explanation. So now, when you then again make a plot or a diagram where you put a band or a region, such that if primordial black holes were sitting in that region, they would explain those events. It's here. So here we have the dark matter fraction versus mass, again in grams here. So if you're in the asteroidal mass range, say, and you have about 1%, so it depends on where you sit, it's something a bit less or a bit more, say 1% in the asteroidal mass range, you could explain those calcium-rich gap transit events, which is, I think, an exciting possibility. Now, some are related. The primordial black holes can also sink in the centers of neutron stars. So suppose you have a light primordial black hole, a light, again, in the asteroidal mass range. By dynamical friction, it would sink in the center of the neutron star, and then at some point eat it up from the inside. This process happens, depends on, depending on dark matter densities and depend on, what masses of primordial black hole you have. But in principle, they could sink in the center. Then you would convert or transmute the masses. So you have a small primordial black hole plus a neutron star, making a mass creating a black hole in the range between 1 and 2 solar masses. So here, I think it worked by Taxikov, Faller, and Kuzenko, who went through the different neutron stars and showed, okay, where would you have sort of a distribution. So this is a distribution which is sort of peaked, I don't know, between at 1.3 or so solar masses. And you could sort of look for those black holes and could, make a deduction of whether this mechanism could have been at work. So, and this actually could also, in turn, produce these R-process elements. So when you, particular gold, so and actually 1 neutron star can produce up to 10 Earth masses of gold. So, and I calculated the current market price. So it would produce 10 to the 30 euro worth of gold. Of course, you need to find it, but you could solve your funding problems by this. And anyways, you would produce a lot of gold, and there seems to be a shortage there seems to be more gold in the universe and a shortage of explanations for where this comes from, as I understood. I'm not an expert on sort of these R-process elements, but it seems to be that there's more gold in the universe than we can explain. But it's primordial black holes going into neutron stars and converting them to bigger black hole, you could actually get more gold and could have a golden primordial black hole age. So, okay, right. So another truly exciting possibility to look for these objects and what they could have caused is when you look far out in the past, and if you look at very high redshifts, and the James Webb Space Telescope has provided us with absolutely an enormous amount of fantastic and phenomenal data, even confirming a galaxy, I think spectroscopically and photometrically confirmed at redshift 14. And that object had less than 300 million years to grow. So, and it's hard to explain this by particle dark matter, but if you come in with a black hole, a heavy black hole, you could actually explain this. And primordial black holes could provide you with a heavy seed, which sort of triggers the growth and fosters the growth of early structures. And these early, and even earlier ones. I will show you what I mean. And also, then on the stellar the mass ratios, which you get, you will, there's some objects which have very little stars around them. And we just wrote a paper, as Zion Zhang was a driving force on this, which can explain actually all of those objects which have very little stars around them, all the black hole. This is actually one of our papers. Is mainly by Zion Zhang. So my role was very modest. So I have to give most credit to my esteemed collaborators here. So what we are looking at, if you have a heavy black hole, a million solar mass black hole, and I will tell you later on why a million solar masses is actually a range where some fraction of black holes could be produced, primordial black holes. It's actually natural to have them there. But if you have those, they could foster galaxy and star formation tremendously. This, of course, depending on the feedback, because very strong feedback, accretion feedback, slows it down a little bit, the star formation. But depending on the feedback, you can actually have star formation much more efficiently going on. And also, yes, and I will come back to this. Now, before I leave my hints section of the talk, let me go to gravitational waves. So these are the 3 observation runs of LIGO, Virgo, and Petra of merging primordial black holes, or black holes have merged and have been where this has been detected. And so now, of course, there's a 4th observational run, which is currently being completed. There's ABC, and then there'll be a 5th observational run. But this is sort of what we have confirmed. And of course, the more and more coming to this. But we have here in these 3 observation runs, we have different confirmed confirmed mergers, and some of them are very happy. So in each of these tile is one of these events, confirmed events. There is the big dot in the middle is the final black hole, and the number is in mass and solar masses, and the small dots or smaller dots are the progenitor black holes with the masses in solar masses as well. So this is the big bummer here is particularly exciting because actually this is in the so-called pair instability mass gap, which says that, so black holes above a certain, let's phrase it differently. So if you want to make heavier and heavier black holes, you need to have a heavier and heavier star, obviously, because you need to make more material. But at some point, when the star becomes so heavy and so hot that you reach this sort of so-called pair instability mass gap, so E plus E minus will be produced, you have a reduction of pressure, and these objects, so above roughly 60-ish, depends on the metallicity, roughly 60-ish, I think up to 150 solar masses, they would explode remnant-less. So you cannot get a black hole from a star directly with 107 solar masses. It's not possible. So it's not possible to get it direct from a star. Of course, you could have multi-merger processes. You could have, lighter black holes produced from stars, and so on and so forth. And then they make up these heavier black holes. But the more we find of these, the more these hierarchical merger channels are put to challenge, I would say. But of course, this is not a disproof of these traditional mechanisms, but primordial black holes can give those to you directly. And we developed a mechanism where this can be achieved very naturally. Now, this was actually a bet that LIGO shouldn't find these in the in the mass gap. I think Sebastian Kless found this bet, and I think it was between Chris Paczynski, Daniel Holtz, and Carl Rodriguez, and Surov Chatterjee. So, and they were betting that, okay, it was a bet was about that you should not have these black holes in pair instability mass gap found with LIGO Virgo Kecker. But you found those, and it's actually a slide I stole from Sebastian Kless, where it actually shows the 2 progenitor masses, and you found and you have sort of the data points here, and of course you have some in the quite heavy mass range also. But of course, our smoking gun for primordial black holes really is subsolar black holes, so subsolar range, because a black hole of 0.2 solar masses, for instance, cannot be generated as the end product of a star. That's just not possible. And we have a few candidates actually, which we found with rather high signal-to-noise ratio, low false alarm rate. None of them is really confirmed, because then it would be sort of Nobel Prize discovery. But we are gathering more and more. I think we have now dozens of these below a solar mass as candidates, like very reasonable candidates, and we just need one to be confirmed, and we can open the bottles, and we will have found dark matter. This is truly exciting. I would guess in the next years we would really see a discovery of these subsolar black holes, and then that would be absolutely amazing for physics, in general, and primordial black hole dark matter in particular. And actually, I was in Cages and with Chris van der Broek, who's in LIGO. I was betting that we will see them in a span of 2 years, and we were actually betting about a bottle of scotch so that's me sitting of course, in a chair in Corsica and Cargés, and Chris as well. We're preparing for our picnic. We probably have the bottle together, but he was betting against. I was betting for it. So let's see who wins. But it's a truly exciting, absolutely exciting time we are currently living in, with high redshift discoveries and with sort of put prospects for low mass black hole discoveries. So so stay tuned. There's something exciting coming, I feel. Right. And since I know my time is sort of I have probably quarter of an hour or so, and this is just right to tell you about my most favorite scenario, which I developed together with Sebastian Kless, Bernard Carr, and Juan Garcia Bido, on where we thought about what could potentially the thermal history of the universe play for a role in primordial black hole formation. And it can actually provide you with fantastic scales. I mean, I will tell you. So stay tuned. So let's step back. So this is actually here the number of relativistic degrees of freedom versus a temperature, right? So the time goes from right to left. So temperature and MEV. So as the universe cools down, so we go with time to the left, more and more particles become successively non-relativistic. So we do have for the top quark and the W and that boson and so on and so forth. So it drops. And when this drops, actually, the equation of state of the universe changes. So in particular, you get pressure reductions. So you have, this is W, a third is radiation, pure radiation fluid, and which is here. And then you get in the sort of, at the heavy masses, sorry, not heavy masses, it's just the opposite. At high temperatures, the electroweak times give you a bump, a dip here in around these temperatures here. The QCD phase transition gives you, or crossover, whatever this may be, gives you a dip here, the strongest one, and then E plus E minus annihilation gives you a feature on this lower temperature range. Now, I told you initially that if you change the radiation pressure, which works against the collapse, you enhance, if you change it to the lower end, so if you lower the pressure, you enhance the possibilities to form black holes. The collapse will be easier. And there's an exponential dependence, because I told you there's fraction collapse horizon patches dependent exponentially on the threshold. So the threshold changes with W, with the equation of state parameters. So we will make it easier when you reduce the pressure to produce these black holes. And this is what you get when you put in basically an almost scale invariant spectrum. And actually what we put in at the different scales, we put in basically something that has the same functional form as primordial power spectrum measured by Planck, at least in the same range. And then we elevate the amplitude. Suppose you have a mechanism that sort of enhances the amplitude. It comes from somewhere, the critical Higgs inflation or God knows what, some mechanism that sort of on the primordial black hole scales enhances the amplitude. Now, and then the different times, electroweak times, make actually, look at this. So the horizon mass during the electroweak times make you a bump around the planetary masses. The QCD scales, because QCD scale, horizon mass around QCD scales around solar mass, they make a peak here, and then you have a peak in the Pion plateau, which is around 30-ish solar masses, and then you have a supermassive mass range giving you a bump, say, at 1 million solar masses. And this is actually the reason why I said 1 million solar masses is actually quite natural, sort of has a natural connection for produced primordial black holes, at least in this mechanism. And again, here we basically took what Planck has provided us, but assumed there's a mechanism to get the amplitude, because we need the amplitude, but all the scales in here are not put in by hand. Let me stress this. All scales here are just provided to us by the universe itself. The well-understood thermal history of the universe provides a peak in the, around the planetary masses, solar masses, tens of solar masses, and the supermassive mass range, which I find quite exciting to get a multimodal spectrum with very characteristic astrophysically relevant scales. this is my most favorite scenario. And now when you look at this is a predicted mass function here, the line here, the black dotted line, and you do have the different regions where we have observations. It's not constraints here. So this is the region from the supernova, which I showed to you. There's another this microlensing event, pixel lensing actually from HSC Subaru. There's the microlensing events here from Ogle. We have supermassive black holes, cosmic infrared, cosmic X-ray background, source abstracted calculation that indicate that black holes should be present. Then we do have pulsar timing arrays. We have another peak point RGB is a pixel lensing survey. They don't see there's tons of positive indications or hints for primordial black holes in the sense that there are observations where primordial black holes would be, I would find a natural, or at least a simple way to explain those observations. So this is truly exciting because it's so natural to explain them, because the deterministic of the universe does almost everything for you, except that you need the mechanism to enhance fluctuations, but it's sort of just enhancing the amplitude. One parameter, if you enhance this, you get a whole plethora of these observations explained. This is super, super, super exciting, and we can't wait to explore more of these. Now, let's see the remaining time, maybe remaining 5 to 10 minutes or so. Let me tell you a little bit about, well, it's from another slide, another talk actually, but let me tell you why I think that the Hawking evaporation constraints are actually not as solid as they appear, at least, or at least in some cases could be weakened or even disappear. So there's been some research lately put forward mostly by Gyadwali, but there are many other researchers as well, but mainly Gyadwali is the driving force here. I put out that actually this semi-classical regime in which Hawking did his calculation, where you have sort of the classical background and quantum fluctuation on top, are left at the latest at half mass of the black hole, at Page's time, say at the very latest. So when the background changed by an order 1 factor. So then you need to have back reaction taken into account. Actually, potentially way earlier, you would get deviations or you relieve the semi-classical regime. And there are indications that actually the black hole evaporation rate becomes suppressed by powers of the entropy. It's not yet clear exactly which power it is, but should be suppressed by the entropy. And the entropy of a black hole is humongous. You have something like, S is something like 10 to the 30 for a 10 to the 10 gram black hole. There's a huge suppression. It's not quite stopping, but it's almost stopping, which is called memory burden effect. But it's actually a general characteristic. If you have objects which carry a huge amount of information, they tend to be stabilized by the information they carry. And the black hole seems to be one of the prime representatives of this category. Now, but of course, if it stops, or if it's sort of basically almost shut down, it leaves a huge a new mass range. You could actually potentially open a new mass window for very light, ultralight primordial black holes, like 10 to the 7 gram or something. And this is only for one case. If this memory burden effect sets in at half mass, but if it sets in much earlier, and there are arguments that it could actually set in at m, over s, or m over square root s, then you could basically remove the entirety of those constraints coming from primordial black hole evaporation. That's totally exciting. A new open mass window, which waits to be explored. It's currently being started to be explored. It's exciting. It's a memory burden effect, which helps. It seems to be an intrinsic characteristic of black holes and other configurations that sort of saturate a maximum entropy bound. So I can tell you more in questions later if you're interested. Now, okay, let me just skip those slides here and talk in the very remaining few minutes on galaxy formation, or galaxy genesis, I called it. So again, this is a slide I had before. where you have a million solar mass, and now I motivated this mass scale. And again, this is a paper by mainly put forward by Zion Zhang, but there's Volker Bohm, and there's Jeon and Liu and Boylan Kolchin, wonderful collaborators of mine. And my role was quite modest in this paper, but we put together this work to see what star formation and galaxy formation looks like when you have this heavy seed. And first of all, depending on the accretion efficiency, that's sort of the different scenarios here, you could form quite compact objects. This is sort of here you see the stellar density versus radius, and in some cases, when the feedback is relatively low, you can get very compact, dense objects here in the so-called little red dot range. You could explain those with the dots, for instance. But you can, given this, we can very precisely calculate what the stellar density is, and then you can see how this compares to what we observe. And this is a truly exciting graph. When you compare this to lambda CDM, I mean the stellar mass here as a function of time, cosmic time. And here we have redshift, and it's in time mega years. And you see lambda CDM basically has nothing produced before redshift 15. But some of the primordial black hole scenarios, where you have the seeds and with a certain accretion feedback assumed, you could start potentially at 30, 50, or even at 100, you could start star formation. So I guess if you see galaxies, we have one at 14, but if you see at 15 or even 20, I think there are candidates at 20, then you cannot really have lambda CDM as I get as an explanation for particle lambda Kodak matter as explanation for those galaxies. But you really need something else, and primordial black holes can easily do this. They can create the highest redshift galaxies. Right, this is the same graph as before. But due to the brevity of time, let me bring up one of my favorite graphs, and also this graph Bernard Carr likes to bring up. It's also credit to him who pointed me to this very nice representation. It's sort of my last physics diagram, which I'm showing sort of the whole mass scales from the Planck scale all the way in logarithmic scaling to the whole universe scale. So, and this is, of course, the snake, Ouroboros snake eating its own tail. You have the microside, the macroside. You can think about it as a clock, with each minute being sort of order of magnitude. And sort of primordial black holes, since they're originating from small fluctuation from the inflationary epoch, say, and producing these heavy structures, even like setting the structures on galaxy cluster scales and so forth. They could be our bridge between the microside and the macroside. So, and this is quite interesting to take primordial black holes as probes of early universe physics in regions where we really cannot access the physics there by other means. So they could also be very helpful if they exist, which I think they do, but if we really find them, we can learn a lot about our early universe. And incidentally, still, it's not for much longer, but still we have the year of the snake in the Chinese calendar. So this is sort of our, this is a connection, there's an anecdote, there's a connection to this diagram. But anyways, primordial black holes could be our exquisite connection between the micro and the macro physics. Now, before I close, let me draw, I have one last thing, and let me draw attention to a meeting. There's actually a meeting which I had in Iceland. We organized a wonderful meeting on black holes and cosmology with a huge amount of people. Which wonderful people who came. There was Lisa Rundle, there was Herman Berlinde. We have Günther Hasinger, many people, and many of those will come back this year. So it's us here. It's on Page, where I mentioned Page's time, and of course Marisa Calariado and as many people. And we will have a new meeting called, again, Black Holes and Cosmology, but edition 2026. in Granada, and that's actually a view from the place we're having. So we have an unobstructed view on the Alhambra. If you look on the internet for Black Holes and Cosmology 2026, we have a website, we have phenomenal speakers already confirmed. And if you're interested, you can look at the website. Registration will be open very soon. You can also contact me. And it will be a truly exciting meeting in June. It will be, I think, somewhere in June, I think 15th to 19th, if I remember correctly. And of course, we would be excited to see you there. So with this, I think I'm at 1 hour of my talk time. And yeah, I hope I could spread some of my exciting for these compact bodies to you and tell you a little bit how they might have formed and what ways are there to explore them and what are the best channels to see them in the future. So with this, I really thank you for your attention.
Thank you very much, Florian. Very nice. Any questions from the audience? Oh, there's a question in the chat. It's a bit long. So he was asking, in models of the primordial black holes, do people usually consider the fact that the background is dynamical, in particular in the early universe? Wouldn't that in many ways affected the stability of the black hole formations or evaporations?
Well, that's a great question, and I think it has several layers to talk this. Of course, first of all, the most basic cosmological dynamics come from the expanding universe. So the universe is expanding. But then, of course, besides that, you have all cosmological expansion, there can be inhomogeneities. So you can have fluctuations and also I showed you the phase transition. Actually, I showed you exactly one of the dynamics that you have. I mean, besides like fluctuations from sort of clustering of overdensities that could, change how the collapse happens, make it more aspherical and sort of prolong it for some time. I mean, we have simulation on individual black holes by, say, Albert Escriva and LMU, I think, and there's also Ilya Musko and friends. I mean, who did phenomenal work on the dynamical formation of a black hole. But of course, if you have the dynamics in terms of the equation of state, for instance, and I think Sebastian Claess and Albert Escriva and other people, I think maybe Fanciullini, De Luca, and Riotto were also working on this, if I remember correctly. There are a couple of people, sorry if I missed some. They were actually taking really into account also the dynamics of the background, because I told you the equation of state of the universe is changing, and if you have those changes going on and the collapse actually takes a while, then those changes must be taken into account, and that actually does affect the primary black hole formation. But those effects can be taken into account, and they in the future they will be taken into account even more, because depending on your level of refinement, you can refine this and make it more complicated, especially when primordial black holes show some original clustering. If you have non-Gaussianities, you can have tremendous clustering, and you can have the peaks, near peaks, clustered, and that could induce another set of dynamics. And there's 2 overlapping peaks that have been studied, but there's more to be done. I mean, we put out a work where we look at the statistics and actually have the finite duration of the collapse and multiple overdensities clustering together. But to resolve this in detail is still ongoing, and it's exciting. But you're right, it's really crucial. Dynamics is an important fact, and that could induce some changes to the black hole mass. If you sort of prolong the formation, suppose you have more overdensities near above threshold overdensity, then sort of this accretion or accumulation process will take some more time. You produce a bigger black hole, but of course you could also produce some non-sphericities, and non-sphericities are also very vital on the formation of these objects, and also the induced spin, for instance, can be calculated. I mean, there's many projects one can do, and they're currently undergone. But just to quickly answer the question, yes, it has an effect and can have a very strong effect. It has partly been taken into account, but there's more which is yet being taken into account. I hope I could answer this question. You can also speak up. I mean, chat. Oh, wonderful, great. I mean, I'm happy to answer questions in the chat, but of course, you can. I think you can speak up also on this channel, right?
Yeah, I think Israel has some issues of his microphone. So I have do you have any other questions from the audience? Maybe otherwise we'll jump in. So I actually have a kind of similar question. So if I remember correctly, like most of these constraints and the estimations of the mass function are based on the assumption that the primordial black holes, when they form, they do not rotate. I mean, they are like non-spinning black holes,
What
right?
do you mean assumption? Can you just say? I mean, you can actually calculate. I mean, when they form, it is okay. Very much dependent on how they form. But by how they form, I mean, what is the environment? These overdensities. Suppose you have inflationary origin of overdensities, and then these overdensity re-enters at some point. And if it's in radiation domination, there are works which have calculated the spin distribution there. And in radiation domination, if you have sort of spherical overdensities and it's Gaussian, then you basically don't have much spin. It changes when you have radiation domination. Meta domination. When you have meta domination, story changes. Or I think if you go to more non-Gaussian or non-spherical situations, that can also induce some rotation, as I mentioned before. But I mean, this can actually be calculated. And also, and let me just mention before you, before you continue, when you have a different formation channel, for instance, I was mentioning quark antiquark pair collision and making a black hole, and there's usually some sort of, say, a random walk going on in the early universe that causes some sort of impact parameter to emerge. There's not head-on collision, but sort of they're slightly not really missing each other. They could miss in some cases, but I mean, it's slightly offset. And the more the offset is, the more the spin will be. And especially the light black holes producing this quark confinement scenario, which Giovanni, Michael Tedeschi, and myself proposed, will be nearly extremely spinning. So you can actually produce basically near extremal objects in terms of spin. Long story short, the formation scenario and by scenario also include the environment that really has a big impact on the spin. But with mostly, and if you have Gaussianity, if you have sphericity, and you have inflationary overdensities making a collapse in radiation domination, you can calculate the spin distribution. So it's not an assumption. You can calculate it, and it's peaked at very little spin.
Okay.
Initial
So
spin.
so that has been taken into account.
Yes, absolutely. But there are scenarios where we could get extremal black holes, basically. Right. And then it's, of course, very interesting because before our talk, we talked about sort of, these horizonless objects. Of course, this would be sort of an extreme and maybe is problematic in other ways, but you could go into the extremal range and have some interesting effects from extremely fast rotation, including, let me just bring it in, because fast rotation in black holes, we have some indications that they made actually a vortex being formed in the black holes. So we did it for toy modes like cetrons. We did it for a black hole analog model, and we found that in this model that we think should resemble key characteristics of black holes. If this object rotates near extremely, there may be a vortex forming inside the black hole. It's a new characteristic, microscopic characteristic that could actually then trap mobile charges, generate magnetic fields. So that's another interesting aspects of extreme rotation. So sorry for bringing this in, but it just came into my mind because it's something which is not so well known, but there may be new characteristic of black holes emerging in when they rotate very fast.
I see. Thank you.
Pleasure.
I shouldn't take too much of your time because you have teaching duty.
Actually, just now, my
Yeah,
students
I
are
know,
waiting
I know, I
for
know.
the
Yeah,
kind of
thank you
history.
very much. Yes, thank you
So
very much. Yes.
thank you for having me. And of course, you can find my contact details on
Yeah.
my publication, and you can just whoever has questions can contact me. So yes, so thank you
Yeah.
very much, and yeah,
Thank you very much. So yeah, let's
goodbye.
thank Florian. Bye.